Hi and welcome back to Podcast School. This is another video podcast in the series of examination questions. Today we're going to take a look back at a paper that was first seen on the 20th of June 2006. It's an AS level paper and it's concerning Unit 3. Okay, let's have a look at Part 1A. A student has designed a steady hand game which consists of a shaped wire and a metal wand. Part of the circuit to control the game is shown in figure 1A, and we see figure 1A here. If the wand touches the shaped wire momentarily, then the output Q will be a high. The output will remain high until the reset switch is pressed. In other words, touch the wand against the wire, Q will go high. If that's connected to a buzzer, then it will buzz, and it will remain buzzing until this reset switch is pressed. So you're told the function of this circuit without having to work anything out at this stage. Part 1 asks, name the arrangement of logic gates shown in figure 1A. So really what we're doing is, they're asking is, what is that? And you should already know, or you should know from notes and from class, that that arrangement is called an SR flip-flop. An SR flip-flop, where S stands for set and R stands for reset. You may have also heard of it just referred to as cross-coupled NAND gates. Either would be correct, but an SR flip-flop is the proper answer there. Okay. Part 2 then, and the table in figure 1B shows the sequence of operations from stage 1 to stage 4 when using the circuit in figure 1A previous. It says, deduce the missing logic states for S, R and Q respectively. So let's have a look at that. Here is a version of the question I've got with the table and also with the circuit, so it's easier to see. So what's the first thing we need to realize then? Well, we're dealing with some NAND gates. So when you're dealing with NAND gates, the easiest thing to do is just actually to write the truth table for an AND. So let's do that. So 0, 0, 0, 1, 1, 1, 1, 0. Okay. Remember that it's the opposite of an AND gate. So an AND would give us a 1 here, 0, 0. Sorry, a 0, so this must be a 1 for an AND. 0, 1 for an AND gives us a 1. A 1 and a 1 for an AND is the opposite of an AND, remember, so that must give us a 0. And a 1 and a 0, well, for an AND gate, that will give us a 0, so for an AND, that's a 1. Okay, so 1 everywhere, apart from when it's 1 and a 1. Okay. Now, let's do something with this circuit. Let's have a think now. What about this wand? What really is it doing in the circuit? Well, you know now that this is a potential divider and this also is a potential divider. Albeit that the resistor in the bottom is either infinitely big or infinitesimally small. The same over here. It's just a resistor. So we've got two resistors. So when the wand is connected or joined, this is a straight connection through the ground, so S will be a 0. Whilst it's not, then the resistance is massive, it's infinite. In fact, it's not connected at all, so it has an infinite resistance. Therefore, S will be a 1. Same with the reset switch. So let's work down through this then. We are told that at the beginning, S is a 1 because it's not touched. So let's put that in. So there's a 1 there. We're also told that the reset is a 1 because it's not pressed. So there is a 1 there. Therefore, let's think what Q, well, you're told what Q will be. It's a 0. But what's the output here? So that's 0, 0 and a 1, remember, because that's a 0, Q's a 0. So that's 0 all the way around. 0 and a 1 must give us a 1. So we'll write that there. So 1 and a 1 is a 0, and that's correct. Okay. Now, it says that the wand is momentarily touched. So yes. So in stage 2, the wand is touched. So there's a short circuit. So at this point then we have a 0 because we're directly connected. So we'll write a 0 in there in black. Okay. Now, this was a 1, so a 1 is still present here. So a 1 and a 0, a 1 and a 0 gives us a 1. So now we're left with a 1 here. Okay. And that 1 propagates round, and 1 and a 1, well, that gives us a 0. So we'll have to make that a 0 as well. Now, a 0 and a 0 gives us a 1, so we're again in a stable state. So Q at that point is a 1. So immediately now we can write this in. So that answer is a 1. Now what about the next state? We're told now that the 1's no longer in contact. So this now must be a 1 again. So S is a 1. But let's follow it through. So if that's a 1, we were previously connected to a 0. So a 0 and a 1 gives us a 1. So that's still a 1. And that ties up with our table, look. A 1 and a 1, that gives us a 0. And now a 0 and a 1 gives us a 1. So again, we're in a stable state. So what are we looking for here? We're looking for S. So that answer, how should I write this in? Whoops. I'll have to do this big R over here. So that answer is also a 1. Okay. Now let's have a look. What are we going to do at next time round? So this time it's still not in contact, but the reset switch is closed. So if it's closed, well then simply that must be connected to ground. So that's a 0 in there. Okay. So the answer we're actually looking for in there is a 0. Now if we follow that through, last time a 0, so that's with a 1. So remember, because I'm looking at the previous state, so a 1 and a 0, 1 and a 0, that gives us a 1. Now a 1 and a 1, that gives us a 0. And a 0 and a 0 gives us a 1. So we're back in a stable state. And look, that corresponds because, look, we've just said Q is a 0. There it is, Q is a 0. And set is a 1. Oh, it's still a 1, isn't it? So that's it. So the answer for that, filling out the table, S is a 1, Q is a 1 over here, and R is a 0. Now in part 3 of the question, you're asked to design an alternative circuit using a thyristor as the main component. Okay. You have to use this circuit to give the same function as before, but you must not incorporate the SR flip-flop. Okay, so it must be a completely new circuit. And look how many points are awarded for this, 5. So this is the main bulk of the question. Okay, let's get a clean sheet of paper then. Okay, so what do we have, or what must we have? Well, remember, we always must have a positive supply, and we must always have a ground. So that's straight away. Let's draw in the bits that we know that we're going to have from before. So we know that we're going to have a wand. Try and draw a wand as best as possible. That'll do for a wand. And we know that we're going to have the bit that the wand moves around. Not quite sure what you call that. The maze, perhaps. And we'll join that in there. Now, we'll put a resistor in here. So that bit's a bit different from before. And we're going to use this as a potential divider. So at the moment, this is a big resistance. It's massive. There's no way the current can flow between this. So you're going to have a large voltage drop across here, and this point would more or less be at 0. Okay, so let's continue on with this. We'll put another resistor in there, and remember we're using a thyristor. And if you remember what a thyristor does, it conducts whenever it receives a gate pulse. So it's a bit like a diode. It looks a bit like a diode. So we'll draw it in, and hold on. Yeah, there we go. And there's the gate. Okay. And it conducts whenever, I said, it receives a gate voltage, or gate current, sorry. In other words, if I attach my buzzer on at this point, let's draw the buzzer in. Sorry for the wonky drawings, folks. There's the buzzer. So at the moment, whilst there's no current pulse with the thyristor, the buzzer won't buzz. But if we were to receive a current pulse here, then it would buzz, in fact. And it would remain buzzing. So how are we going to create this current pulse? Well, the way this is actually set up in the minute will do, won't it? At the moment, as I said, there is no connection here. But if we simply were to connect these two together, as would happen if the one touches the other part, then we will have current flowing. And we'll have current flowing not only down through the resistor, but also in this direction, which will be enough to give us our pulse. So that pulse will switch on the thyristor. It's already forward biased, so it will conduct, and the buzzer will sound. Now that's great, that's exactly what we want. But we also need a reset switch. So the best way to reset a thyristor is simply to short circuit its two terminals. So all we have to do therefore is draw in a push to make switch in that direction. Okay, so now even if the current, well, after the current pulse has disappeared and we push the switch, the thyristor will turn off. So there's bits of the circuit we need to label here. We need to make sure that this bit is called the set. We also need to make sure that we've labeled our reset over here. And then label all the other components. So label the buzzer, I'll just call that the TH, but you know what I mean. You must label the thyristor. And that's about it. Just put on, I would maybe always put on VCC. I would write ground down here. Alright, and it wouldn't help to have a short explanation of that. Okay, so that's the circuit we're looking for.